Okay, so for this reaction, this is also a photochemical reaction. This is also another isomerization. So when we look at the start material and the product, hopefully you could make the connection between the different structures, that these two carbons in our start material become these two carbons in our product. So the photochemical aspect of this reaction, obviously we've got some carbon-carbon pi bonds in our aromatic rings, but more often than not, but also controlled by the wavelength of radiation, the excitation will be of the carbonyl. So if we draw our curly arrows showing movement of one electron to give us our diradical, the first intermediate would look like this. So we have our diradical species from the photochemical excitation of our carbonyl. So when we look at the relationship between start material or now intermediate and product, you can see that we have to remove a hydrogen from this carbon, and we've got to get a hydrogen onto this oxygen. So we're going to abstract one of these two hydrogens. They are chemically identical. Let's pick this one. And that will then give us our next intermediate. So now we've gone from a diradical on carbon and oxygen to now a diradical both on carbon. And you can see the structural relationship between these two, that all we need to do is connect those two radicals to get us to our product. So mechanistically, we're able to draw our curly arrows to show the formation of the product. Again, we can make sense of what's happening. The excitation is the N to pi star of the carbonyl. Hydrogen abstraction occurs again conveniently because of the location or proximity of the oxygen radical to the hydrogen. And also abstraction of one of these hydrogens gives us our significantly resonance stabilized radical.